Okay, Assalamualaikum and a very good day. So we are still in the isentropic nozzle flow and we are in the part 3E. Okay, and for this isentropic nozzle flow, we are going to see two type of nozzle. Okay, either the just a converging nozzle, okay, in the first case, and then later we are going to look on the converging diverging nozzle. So the most important effect is on the mass flux. Okay, we want to see that whether we can actually have a greater mass flux. So how we can actually increase the mass flux, okay, with the influence of the reservoir pressure and also the receiver pressure that through that is for the nozzle, okay, related to this nozzle flow. Okay, and the first part that is on this converging nozzle. So we will look on the converging nozzle first. And for the converging nozzle, we can analyze two effects. One is reservoir pressure and the receiver pressure. But I will start on the effect of the receiver pressure on the mass flux. Okay, so this is effect of reservoir pressure with the mass flux. So in order for us to increase a mass flux, okay, in the very initial case, okay, when you don't have any change or you don't have any pressure different between the reservoir and the receiver, you are not going to have any flow, right? Okay, it's example like the valve here. If you have a valve here, it's closed. Okay, so you don't have any flow, right? So when you open suddenly, you open slowly the valve, so you are going to reduce the pressure, the receiver pressure, okay, or the back pressure here. Some of the boat you use a receiver pressure, a back pressure. Okay, when you reduce this pressure here, the receiver pressure or the back pressure here, you are going to get the flow. Okay, the flow that from the reservoir to this nozzle. Okay, so here everything here reservoir condition we held is constant. Okay, all these properties at the reservoir is held constant, so we just reduce the PR. Okay, so you can get the flow inside the nozzle. Okay, so this is actually when I said there is no flow, when the ratio is equal to 1 sim, so you don't have the flow, only you have the PR is getting less, so you can have the flow. So with the flow, okay, with this effect of the PR, reducing the PR, so you can get the increase in term of the mass flux. Okay, so we can see from this line, okay, you see this left curve on the, okay, for this part, for this reservoir pressure effect, we see this left curve here, from here to here, this is the left curve. So this is in terms of the pressure, the receiver pressure to the reservoir pressure. Okay, reservoir pressure is constant. Okay, so we decrease the reservoir pressure, so we can have the increase in terms of the mass flow, okay, through the nozzle. Okay, until, okay, we have this the ratio here. Okay, this is actually the critical ratio. This is also, you can see back from the previous part, where this is actually a P star over the P naught. Okay, because we have this PR, so we put is a PR, or it's actually a P star over the P naught. So you get this ratio of 0.5283. So this is only, you can get the ratio if this is the airflow with K equal to 1.4. Okay, so you can have this number. Okay, so it means at this flow, we know that is actually at a critical area, so that is actually at the exit or the throat of this nozzle, so you can get this maximum pressure, maximum mass flux, okay, at this point. So whenever you decrease the further decrease this reservoir pressure, the receiver pressure, when you further decrease the receiver pressure, you are not going to get increase in the mass flux. Okay, the mass flux will not increase. So it's no point you are actually decreasing the pressure. Okay, maybe we need some mechanism to decrease the pressure. So it's no point just wasting your energy, okay, or your power consumption or whatever. So because you are not going to get a maximum mass flux. Okay, so you cannot, maybe in the performer, you cannot increase the power of the device anymore because you're already at the maximum mass flux. If you have like the fuel, okay, it's actually a maximum flow. You cannot increase more the fuel. So, so we call it at the choke condition here. Okay, so you don't have to to decrease the back pressure anymore, or the receiver pressure. Okay, because the mass flow, the mass flux or mass flow rate will not increase. So this condition we call is as the choke flow, where we can achieve the exit, the Mach number at the exit equal to 1, okay, or equal to unity, okay, 1. So there can be no mass flux increase, okay, at the Mach number equal to 1. So it's called a choke flow. This is happen with the when we are lowering the receiver pressure, okay, with the effect of the receiver pressure with the flow rate. Okay, so this is just now I mentioned that if we were to reduce further the PR below the critical pressure, so there is no effect on the upstream flow. Okay, this is the upstream flow from the reservoir. Okay, the flow you cannot push it more. Okay, it's actually maximum mass flux, okay, or mass flow rate. So this is the case of the converging nozzle on the effect of the receiver pressure. So this receiver pressure is actually at the back here, or you call a back pressure. Okay, where you held all this reservoir condition, or this upstream condition here equal to constant. Okay, there is no change in terms of the reservoir condition. Okay, so that is the first case where we look on the application. Okay, and another one, if we want to see on the reservoir pressure. Okay, we held the receiver pressure constant. Okay, so we are going to increase the pressure. Okay, there is two ways we can actually be able to generate the flow inside this converging nozzle. Either we can reduce the PR, okay, at the back here, okay, whether this is all constant, or we can actually increase the reservoir pressure and we held the receiver pressure constant. Okay, so same thing also. So this is, we are going to look on this curve on the right side here. Okay, this blue curve on the right side here on the effect of this reservoir pressure, that is the P naught. So when we have the ratio equal to 1, there is no flow. Okay, but if we further increase the P naught, so we are going to get a flow, okay, that go through this nozzle. So until certain extent, okay, so this is actually we can get this choke flow. Okay, this is actually just the reciprocal of the P star equation with the P naught. Okay, when you make a reciprocal P naught over the P star, so you are going to get this number. Here is this original. Okay, this is just the opposite one, the reciprocal of this ratio, so you get this number. So it can be a choke flow also at this exit condition here. Okay, where the ratio of the P naught over the PR is about 1.893, the value. Okay, so that is we can also have the choke flow also at this condition. Okay, but if we increase the P naught further, okay, we can expect an increase in term of the mass flux. Okay, even though it's already choked, because at this time the P exit is actually less than the PR. Okay, so you can expect there can be the increase in term of pressure, because we know actually the air is very light. So it's actually, it can if you go to the textbook, it said that it can actually turn sharply. Okay, so you can actually can increase the flow, okay, when you actually increase the P naught further. Okay, so because we said that the flow is very light, so it can increase sharply, so we can expect the increase in term of the mass flux. Okay, provided that the PE is still less than the PR. Okay, PX is less than the PR. Okay, but if you were to have the you increase more the reservoir pressure, it can be the condition where the PE is greater than the PR. Okay, so at this condition, it will break the line here. Okay, if you attach here with the pipeline here, so this is actually the cause of the pipeline rupture, because it cannot withstand anymore with this increase in terms of the pressure here. Okay, and also the mass flux. So because it's already the some of the mass flux is already turned sharply. Okay, at this condition. Okay, so it can make the pressure at the exit is greater than the PR, so it can have this gas pipeline rupture. Okay, so this is very undesirable effect. Okay, so we want to have this effect, so so we need to know what will be the maximum P naught that we can increase in order to have the mass flux. Okay, so that's all on this actually the this converging nozzle. So in the next part, we will see on the effect of the converging diverging nozzle, but the only parameter that we are going to vary is only the receiver pressure. So that's all. Thank you very much. Assalamualaikum.